Okay, my goal is to talk about the classic thermal expansion demo you see in class, where you have a brass sphere, and you have a brass ring, and then the brass sphere is just slightly smaller than the ring, and you can see it sticking a little bit there, but if you get it lined up just right, it should go right through, but just barely. Now, the dimensions, this is on page 65, problem 18.4, volume 3, and I'm going to focus on part B. There's a couple other parts asking you about density and stuff, but let's just focus on the thermal expansion part. And so this is the inner diameter of the ring is 23.9, and the outer diameter, well, the diameter of the brass sphere is 23.6. So that's why it's just barely able to go through like that. And then I looked up the coefficient of linear expansion. If you remember from last time, just as a quick reminder, let me scroll over to this board. So this was our thermal expansion information. If you want to pause the video and refresh your memory on that, you can. Maybe I'll turn this off so you get less glare. But so I'm going to come back to this board now. All right, so I looked up this value, and I got 19 times 10 to the minus 6, 1 over degrees Celsius. Remember, because the equations use a delta T, we can use Celsius, degrees, and Kelvin interchangeably for delta T's, not for T, for delta T. Okay, enough on that. A quick comment. If you look around, every book might give you a different number here, or every teacher, and you might be saying, wait, you're wrong. Look, what we're doing is only a ballpark estimate. Every book and teacher may have a reason to use a different value. Maybe they're using different temperature range. In this room, it's about 20 degrees C, and I'm going to heat it up from there. But maybe some other teacher might say, well, I'm going to use the average value at a higher temperature because on average the ball is spending most of the time at the higher. So there's valid reasons to use different numbers here. If you need to be precise, that's a different thing. You can contact the manufacturer or a vendor and get specs, or you could take this to another level. But for this class, just use the numbers I give you, and if they look a little bit different in a different book, don't sweat it. Just use the values and realize you might have differing answers in maybe the second sig fig for some of these problems. All right, so now here's the question. The sphere can fit right through there, but I'm going to take this and heat it up with a blowtorch here in a minute. All right, and I'm going to see at what temperature will this no longer fit. So I'm going to heat up the sphere until it no longer fits through the hole. So what temperature should I use? If you want to try and do it yourself, maybe pause the video. I'll put the equations on screen for another split second. There they are. If you want to try it yourself, pause the video and go. I'm going to do the answer in 3, 2, 1. Okay, here we go. So I know I want, let's just give this a variable. Let's call this D. And maybe we could call this inner diameter here capital D. It's a little bit bigger. So we want D to equal, I should be careful, D prime to equal capital D. In this case, D prime, you could say, is D naught times 1 plus alpha delta T, and that should equal D. Now another way you could do this problem, you could also instead say delta little d should equal the difference between the two. All right, and maybe I'll call this D naught, where that's the initial diameter when it's unheated at room temperature. Everything's at room temperature in here right now. So, and if you look, what does this equation give me? it's pretty much the same thing. Take a look here. If you actually, distribute this through and rearrange it, you get this result. So I'm just showing you that you could either use the change in distance should be the difference, or say the new diameter should equal the whole diameter. Either one will give you the same results. So from there, I'm gonna basically work with this one. All right, and so what were we looking for? We're looking for, I think I want the temperature. Determine temperature at which sphere no longer fits through hole. So that's what I want to learn about. If you want to pause the video here and go for it, try it. I'm going to work on it in 3, 2, 1. All right, so we're looking, I'm going to try to solve for delta t first. So delta t should equal this thing divided by that. Now, I could check the units really quick. Meters, meters, this is meters, this is meters. This is 1 over degrees Celsius. When you flip it, we should get degrees Celsius. This is looking good. I could go one step further. This is T final minus T initial. I'm going to drop the color coding now. Where T initial is whatever temperature we're starting at, room temperature. Let's assume T initial is 20 degrees Celsius. Well, okay, so look, if your teacher ever says room temperature, a common assumption for room temperature is about 20 degrees Celsius. Every room's a little different. If you need to be precise, you get out a thermometer. But if we're talking about room temperature problems, just assume room temperature is 20 degrees Celsius unless otherwise specified. All right, so rearranging this, we should get T final is equal to the initial temperature plus, I guess I am going to color code it. Sorry. Can't help myself. All right. And then if you do the math on this, plugging in all these numbers, what did I find? I think I found 689 degrees Celsius. So if you want to pause the video for a second and make sure you get that number for T final, go for it. A common mistake is to forget to add the 20 from room temperature. So if you ended up with 669, you might be like, what? Remember, we solved for delta T, which is the change from room temperature. So you got to remember to add in that 20. Double check for that. And then I'm going to go ahead and do the demo. I'm going to make sure where's my remote? There it is. All right. And where was my numbers here? Just making sure, I just want to confirm I got the right number written on the board. Okay, cool. All right. So let's see what happens here. So again, no longer fits through there. Gonna heat it up. And this demo does give you an idea of how ridiculously small these expansions are, right? I'm heating this thing up with a blowtorch. It still just barely, almost fits. Let's get a little bit warmer. So this thing is really hot, right? And you don't notice the expansion at all, but then when we try to put it through the ring, it no longer fits. And just to prove that, now, it's just barely, not quite there. It's heated a little bit longer. So an interesting thing, you can think about this. I'm going to heat the sphere until it no longer fits, and then I'll hold it like this. And then I'm going to allow what's going to happen as this brass ring gets heated up. What should happen to the size of the hole? as these two come to thermal equilibrium. So it no longer fits, right? But right now the brass ring is heating up, and I'm going to speed this up. Oh. If we heat up the ring, what's going to happen to the size of the hole? It should get bigger eventually, and the sphere should fall right through. So, geez, this is a boring video. It's starting to get there. All right, let's go ahead and just let this. Eventually, we should be able to get this through. Boy, this is a slow video, huh? Oh, there it goes. All right, so just showing you the size of the hole does increase as well. That's a